So let's get started. So we are aware of人家来观课的时候人太少才可以看，应该这时候安排 quiz， 真是太糟糕了。我 I don't care， 对啊，就是其实来不来听我的课都没关系，如果你们可以自学的话，那个对啊，我自己以前都是自己看，我觉得自学很不错。Anyway, okay, that's the other direction. If A has n independent eigenvectors, okay, so if A has n independent eigenvector, then that pretty much means like that n eigenvector to be x1, x2, xn. These are their eigenvectors, and the corresponding eigenvalue lambda 1, lambda 2, lambda n. Okay, so then, if that's the case, then that means according to the definition of eigenvalue and eigenvector, it means A x1 equal to lambda 1 x1. A lambda ax2 equal to lambda 2 x2. Dot 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 dot. A xn equal to lambda n xn. Right? Right? And I can write them all together. So A times, this is x1, x2, xn. This will be, this is like lambda 1 x1, lambda 2 x2. Lambda n xn. So you have like these column vectors, column vectors, column vector, equal to these column vectors, column vectors, column vectors. And then, okay, this one obviously is equivalent to, if you name this one as x, then this thing will be x times b. Right? Okay, but not done yet. We're not done yet. Almost. It's almost. Ax equal to xt. Okay. But we need to show A equal to sorry. Yeah. We need to show B equal to x inverse AX, right? But how do we know the inverse of x exists? You need to argue that x is non-singular, right? X is non-singular, right? But this is a given. Why? Why? Because, okay, we know x has n column vectors that these column vectors are eigenvectors. And we know these eigenvectors are linearly independent, right? What does that mean? It means the rank of axes, right? The rank of axes, in other words, okay, if you still remember what we discussed earlier, that indicates x is non-singular, so x inverse exists. So we can write. Okay, we need to have this argument. If you do not have this argument, you cannot have x inverse. Okay, this is very important. So from here, then we can get like d equal to x inverse ax. Okay, you need to argue. You need to explain why x inverse exists. Okay, once you are able to do that, then obviously we have the final result. And according to the definition of diagonalization, yeah, x diagonalizes a, yeah, x is diagonalized, so a is diagonalized. Okay, so that completes this theorem proof. Okay. So any question? So far so good. 上一堂课还比较多一两个。现在1、2、3、4，不算那个助教的话，4个人，助教2个，你们只比助教多1倍而已。对啊。就是快要变成家教班了。Okay. So here's an example. Okay. You can, because I don't know if I can finish this chapter. I'll try my best. To be honest, this semester is already like the best semester. In the sense that I can probably teach like more material. In the past, I wasn't able to finish this chapter. I was usually only cover up to somewhere here, okay, or like the middle of next section. But I think this time I can cover most, probably if not all, but most of this chapter. Okay, but I need some help. For example, like this type of computation, I probably just handle those things. Because this computation, you know how to do that, okay, and you can solve this by yourself. The characteristic polynomial, and you get lambda to be 0 and 1, and then you can compute like its eigenvectors, corresponding eigenvector. So, the x will be, you see, 1, 1, 1 is like, the column vector will be, it's the eigenvector. 1, 1, 1, 1, 2, 0, and 1, 0, 1. Okay? And the x inverse, you can compute that yourself. And the diagonal matrix is going to be 0, 1, 1. Okay? Based on the order of this column vector. Okay, so 0, 1, 1. Okay, in the diagonal. So the next one, an n by n matrix A has fewer than n linearly independent eigenvector. If that's the case, we say that A is defective. An defective matrix is not diagonizable. Okay. Um, so I mean, you can try to verify. Okay. These two matrices, they are, you know, defective in the sense that they do not have n linearly independent eigenvectors. Okay, but again, I will hand wave this part. I mean, like I said, I mean, the first one is like, you know, the eigenvector is 2 and 4. Okay, the second one eigenvector is also 2 and 4. I mean, because it's like a, you know, lower triangular matrix. So you know, like it's very easy to compute like determinant. You know, just like you know, modify like the diagonal elements. You know, so it's like 2 minus I times 4 minus I times 2 minus I. So obviously the root of this characteristic polynomial is 2 and 4, and you can solve like corresponding eigenvectors and see like if they are linearly independent. Okay, but I will let you guys do that. I mean, this is like a pretty straightforward. Okay, basically just show that these two cases. I mean, you know, I believe one is effective, one is non-effective. Okay, but I don't remember which one is which, so you can check it out by yourself. Okay. So this type of question I may ask like in the quiz, okay, or like in the final exam. Okay. So you need to remember. I mean, if you, some people ask me, okay, why a defective matrix is not diagonizable? Remember, okay, I mean, remember, this theorem is if and only, right? If you have n linearly independent eigenvector, I mean, I already showed you how we can construct the diagonalization, right? Right? So that is why, okay, you know, if it does not have like a linearly independent eigenvectors, it's not diagonizable. Okay. Otherwise, we have some issue. Okay, it's not, you know, because this is the only. Okay. Okay. The last thing in this section, okay, it is like kind of interesting, and there are so many applications and extensions for that. Okay, it's polynomials of matrices. Okay, if you have a P of X to be a n x n plus a n minus 1 x n minus 1 blah 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 plus a 0. This is n degree polynomial. Okay, and A is an n by n matrices. We can, you know, compute a P of A, which is a n x a to the power of n plus a n minus 1 times a to the power of n minus 1 plus blah 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 plus a 0 times the identity matrix. Okay, that's the result. But obviously, okay, you could imagine there's a lot of computations involved, right? We multiply like a matrix, you know, for a n, you multiply matrix n times. Okay, I mean even for 2 by 2 matrices, multiply like a 2 by 2 matrix, maybe like with like if m is for example 3 or 4, it's already a lot of work. Okay, something that can help us. Yes, if A is diagonalizable, okay, then we can write D equal to x inverse AX, right? So if D is x inverse AX, obviously A can be represented by x dx inverse, right? Right? So with that in mind, okay, P of A is going to be, this one, because the AN x plus AN minus 1 x n minus 1 plus blah 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 plus A0 I, and this is like a P of x. Sorry, P of A. But this one, okay, if you try to write A as x d x minus 1, okay, it will become x d x minus 1 times x d x minus 1 times times x d x minus 1. 2 is n times. Right? For the first term, right? And you will be surprised to find that x inverse and x cancel out. This cancel out, this cancel out, this cancel out. So, I mean, effectively, it becomes AN x e to the power of n x inverse. Okay, I mean the first term. I mean the other part I didn't write, but the other part has similar logic. So what is d to the power of n? D to the power of n, because D is a diagonal matrix, right? Diagonal matrix, if you try to compute it, you will find that, D to the power of n will be, if D is like that, then, D to the power of n is going to be lambda 1 to the power of n, lambda 2 to the power of n, lambda n to the power of n, all the other are still 0. Okay. So in other words, P of D, okay, is going to be like that. So it's very straightforward. Okay. So you can compute this one equal to AN d to the power of n plus AN minus 1 d to the power of n minus 1 blah blah blah. I mean, you can get an x and x minus 1 out. I mean, one from one and back. So the middle part will become P to the power of P of D, okay? And then, once you get D, basically you can compute like P of lambda 1, P of lambda 2, and so on. As a diagonal element, and then that's the P of D, and then you can multiply x to P of D, and multiply the result to x minus 1, and that will be P of A. Okay. Still a lot of work. I agree. And it's still a lot of work. But, okay, when the power of n is large, this is obvious, justified, right? Here is an example. Px equals x squared plus 3x plus minus 2. We want to compute P of A, okay, which is A is like that. Okay, if I were you, if you see this one in an exam, I suggest you directly compute. Just compute like a to the power of 2, okay, a times a plus 3 times a minus 2 times identity matrix. That's quick, right? That's not too much time, right? It doesn't take much time. But if you want to do it like in this manner, yeah, you need to first diagonalize this a. You need to diagonalize a, and then convert a into x dx minus inverse. So it's going to be something like that. Luckily, it's 2 by 2, so it's not that much effort, but still, I think you can just compute it directly. Okay, I think that's easier. But anyway, okay. So once you represent a equal to this one, then P of a is going to be x times P of d times x inverse. P of d is like that. So it's so the result is like that. But honestly, I really think that you should and there's I think there's some computation error here. Okay, I think this I suggest you to do it by yourself. I mean, as a practice, just as a practice, because I think this is wrong. Okay, because like you see, x is this one. X inverse